What is a wave? A wave can be described as a disturbance that travels through a medium, transporting energy from one location to another without transferring matter. To help better understand what a wave is, let's see some examples of the different parts of a wave. The amplitude of the wave is the maximum displacement of the string above the equilibrium position. The wavelength is the distance between two successive points that behave identically. The crest is the maximum height of the wave, and the trough is the minimum height of the wave. One type of a wave that is seen in guitars is a standing wave. A standing wave must have 2 points that are fixed, called nodes, and at least 1 point that is vibrating, called an antinode. When two waves are traveling down a rope that is fixed at both ends, it is reflected back inversely. The result of this is a wave that looks like it is not moving, but has twice the amplitude of the original wave. The most common type of standing wave is a guitar string. If you let a guitar string freely vibrate, it will create what is called the fundamental wave. A fundamental wave has 2 fixed nodes and a single antinode in the middle. If this guitar string were 10 centimeters long, the wavelength would be 20 centimeters. Because the fundamental wave is half of a wavelength, so the wavelength must be doubled. As stated before, the fundamental wave has 2 fixed nodes and a single antinode in the center. If you add a node, it will create a second antinode. This is called the second harmonic. Every subsequent addition of a node will create an additional antinode, resulting in the third, fourth, fifth, all the way to the nth harmonic. The wavelength of each harmonic is given by the following equation. Wavelength equals 2 times L over n, with n being which harmonic is described. As previously shown, the wavelength of the fundamental wave of a 10 centimeter string is 20 centimeters. Using this equation, we found all subsequent wavelengths with the same 10 centimeter string. The second harmonic has a wavelength of 10 centimeters, the third harmonic 20 over 3 centimeters, the fourth 5 centimeters, and the fifth 4 centimeters. Using this equation, you are able to find the wavelength of any number harmonic given the length of the string. Each guitar string gets gradually thinner towards the bottom because waves travel faster on a tighter string, creating a higher pitched note. Also, the denser strings have a lower pitch to them because the waves cannot travel as fast. Tuning the guitar changes the tension, which will consequently change the sounds. The speed of the wave equals tension divided by mass density of the string. V also equals frequency times wavelength. These two equations mathematically prove that changing the tension and density of a string affects the frequency of the waves, thus creating a different sound.
Let's go back to the previous video, which demonstrates the standing waves in a guitar string. You can clearly see the waves in a guitar string when it is plucked. If you look closely, you can see the slight differences in wavelengths that vary between each string. The difference in wavelengths is caused by the different tensions in each of the strings.
Frequency is how air molecules vibrate after the waves of a guitar string set them in motion. These vibrations are what create the desired sounds. The quality of these sound vibrations, or timbre, depends on the natural frequencies. The 2 tones most commonly used in music are pure tones and rich tones. Pure tones vibrate at a single frequency, while other sets of frequencies, rich tones, have a whole number mathematical relationship between them. These frequencies all meet at a certain point. It is called consonance. Here we have an example of consonance where all 3 of the notes meet at 2 pi. Frequencies that do not have a mathematical relationship create noise rather than music. This is called dissonance. Here is an example of dissonance where the frequencies do not all meet at a single point. Beethoven, even though he was deaf, was a world-renowned composer. How did he compose such beautiful music despite being deaf? He used physics! As discussed before, consonance uses the mathematical frequencies and vibrations to create music. Beethoven used this to know what sounds make sick beats. One of Beethoven's most popular compositions, Moonlight Sonata, is an example of how he used his knowledge of the relationship of frequencies to accomplish this. Guitars and other musical instruments are not the only common everyday objects that use waves. Waves are also found in microwaves, and we all know college students can't live without those. Radios, X-rays, ocean waves, light, and Beethoven's famous hairstyle.